Good day, colleagues. Thank you for the honor to present the results of our work. My talk is about the lost opportunities model, that is a new approach to analyzing, monitoring and forecasting the official statistics of the coronavirus epidemic. The research was done by 4 scientists from Russia, Moldova and Romania, listed here. A few words about modeling techniques. There are 2 modeling approaches described here. We used the second approach based on the following idea. We know the analytical solution of the model and find the parameters of the model so that the solution approximates the experimental data as precisely as possible. Let's see this technique with an example, a ball flight over the surface of a planet. We may not know the acceleration of gravity on this planet and the parameters of the throw. It doesn't matter to us. Because we know, the ball will move along a parabola. Suppose we have some experimental data, timestamps and the corresponding coordinates of the ball. Then we simply draw the parabola as closely as possible to these coordinates. The well-known parabolic regression algorithm is used. Then we can analyze the movement process, calculate angles, speeds, gravitational acceleration, etc. Then we can make predictions. We can calculate the start, top and end points, ball coordinates at any given time. We can monitor the process. When new data comes in, we check that the new points don't deviate much from the parabola. We also recalculate the parabola to more precisely describe the true path of the ball. What if the new points deviate greatly from the parabola? Obviously something happened. We need to accumulate some new data and calculate a new parabola. The ball has lost the opportunity to fly along parabola A. The ball now has the opportunity to complete its flight along parabola B. Let's remember these terms, lost opportunity and current opportunity. This simple example is a good illustration of the technique we used. The subject of our research. Let me emphasize that we are modeling, monitoring, forecasting official statistics, not the true epidemic process. We understand that this data is far from true data about the epidemic. But we have no other data. Official sites are the source of primary data for the model. Every day, the number of coronavirus cases, the number of recovered and the number of deaths are extracted from the site. These values are noted by the letters V, H and D, and the timestamp is noted by the letter T. Secondary data are calculated on the basis of primary data. P, the number of people who have finished getting sick. S, how many people are still sick, this is the burden on the healthcare system. Finally, 7 days average velocities are calculated for all values. The velocity for some value is denoted by the same letter as the value prefixed with or undercase letter, V, the first letter of the word, velocity. Many mathematical models of epidemics are known. We chose the simplest one because we don't have reliable primary data, so the use of complex models is pointless. So we are using the SI model. This slide shows the differential equation of this model and the analytical solution to the equation. Let's emphasize that this differential equation and this solution describe any self-accelerating process in a field with limited resources, not only an epidemic. The term self-accelerating process means that each single event generates several other similar events. The words field with limited resources mean that there are resource limitations that don't allow the infinite expansion of the process. So, the process will stop, reaching a certain size unknown to us. Let's set some values for all parameters and plot the graphs of an epidemic according to the SI model. This slide shows volume graphs. V, the number of COVID cases, S-shaped blue curve. E, the number of people who finished getting sick, recovered or died, green curve. S. Difference between V and E. How many people are still sick? The burden on the healthcare system. Red curve. Key events are marked on the curves: maximum burden on the healthcare system, the last COVID case, the end of the epidemic. Each key event defines a timestamp and value for the corresponding variable V, E or S. This slide shows the graphs of the velocities. Key events are marked on the curves. The maximums of the velocities. The point where VV becomes small enough, less than a certain threshold value. The point of intersection of VV and VE. The point of intersection is important. After this moment, the burden on the healthcare system is continuously reduced. The most interesting thing is the plot of the phase plane, when the x-axis is the number of cases, and the y-axis is the velocity of the number of cases. The differential equation has a quadratic polynomial in V on the right-hand side. This means that the plot on the phase plane will be just a parabola. The left root of the parabola, 0, 0, describes the beginning of the epidemic. When the number of cases was 0 and the velocity of the number of cases was also 0. The right root, n, 0, describes the end of the epidemic. When the number of cases reaches a certain limit n, the epidemic will end, the velocity of the number of cases will be 0. We don't know this value of n, but it exists and it can be calculated as the right root of the parabola. Now it is clear how the process of modeling using the SI model works. It's like analyzing a ball flight. We plot the points of real COVID statistics on the phase plane. We then compute a parabola that closely approximates these points. This is just a parabolic regression, but the left root of the parabola is set to 0. As a result, we find out the parameters of the model n and a. Then we choose the remaining parameter tau so that on the plane t, v, the solution to the differential equation, that is, the hyperbolic tangent, passes through the latest t, v, pair of statistics. By extending the hyperbolic tangent into the future, we get the forecast of the SI model. After that, it is easy to find all the key events of the epidemic. This is how modeling, analysis and forecasting works. Now let's discuss monitoring. New statistics come in every day. Every day we repeat all the discussed calculations and get new updated values of the parabola parameters a and n, updated tau, new forecast, and new values of key events. One day we notice that the parabola don't approximate the statistics as precisely as we would like. After 50 days, the results of parabolic regression are no longer good at all. And on the plane t, v, with a hyperbolic tangent, everything is really bad. What is the problem and how to solve it? Obviously, the equation that holds true for all self-accelerating processes in a field with limited resources is violated. And the epidemic leaves the parabola a at point x. We have already discussed a similar situation in the ball flight model. But what happened to the epidemic? The epidemic was, is and will be a self-accelerating process. So only the second condition could have violated, I mean, the amount of resources available for the epidemic has changed. At point x, the epidemic restarts on the field with a new resource limit. This restart occurs from a non-zero level. It means that when the epidemic leaves the previous parabola, it's necessary to build a new parabola with free both left and right roots. In the same way as it was done for the ball flight model. The epidemic has lost the opportunity to travel along the parabola A, ending with 200,000 COVID cases. The epidemic obtained a new opportunity to travel along the parabola B, ending with 430,000 COVID cases. The whole epidemic history is a chain of transitions from one opportunity to another. That is the main idea of the lost opportunities model. The further modeling process is obvious. Having the new parabola B with two free routes in the phase plane. We select the tau parameter in the same way as before. We calculate the hyperbolic tangent in the plane t, v, to create a forecast for the future. We calculate all key events, and save their parameters. Then we are waiting for new data to continue monitoring, analysis and forecasting. The reasons for the loss of opportunity can be very different. Some of them are listed here. But these aspects are out the scope of our research. It is important for us that the model allows to automatically determine in real time when the epidemic is developing naturally according to current opportunity and when there is a transition from one opportunity to another. This model is extremely simple. Calculations are performed every day when new data arrives, and calculations include parabolic regression to determine the current opportunity with the maximum duration from the current day to the past. Direct calculation of the forecast and all key events of the epidemic. Another important point in our methodology is the so-called forecast drift. We accumulate time series and draw charts that describe how our predictions change from day to day. I mean predictions of key events which describe expected volume, velocity, and timestamps of forecasted key events. In fact, this allows us to predict changes in our forecasts regarding the volume, intensity and duration of the epidemic. So, this is a prediction of forecast changes. The model is applied to the official statistics of Moldova, Romania and Russia. This table summarizes the main current forecasts of the COVID epidemic in these countries. The percentage row indicates that Romania is completing the epidemic in terms of forecasted new cases. The dates in the bottom two lines confirm this. Moldova is also completing the epidemic in terms of forecasted new cases, but the completion dates are longer. This is due to the very low current and forecasted intensity of the epidemic. Russia is very far from the end of the epidemic. This slide shows the current and lost opportunities for Russia. Russia found a new opportunity on June 9. In fact, it's the third wave. Current calculation of epidemic volumes for Russia. We see key events and growing burden on the healthcare system. Drift of the forecast of volumes for Russia. The forecast drift for the final number of cases was very small in this winter. Then we see a turbulence zone. Drift of the forecast of dates for Russia. The forecast for the dates of many key events has been worsening since June 19. The current and lost opportunities for Romania. Romania is firmly moving along a steep parabola towards the end of the epidemic. Current calculation of epidemic volumes for Romania. The key event, low enough velocity, has already happened. The two remaining key events are coming soon. Drift of the forecast of volumes for Romania. Everything has been stable since spring. Drift of the forecast of dates for Romania. Also, everything has been stable since spring. The current and lost opportunities for Moldova. Moldova at the very end of the steep parabola has passed from it to a small low parabola. It results in an increase in the time of epidemic at a low its intensity. Current calculation of epidemic volumes for Moldova illustrates this. Drift of the forecast of volumes for Moldova. Everything has been stable since spring. Drift of the forecast of dates for Moldova. Dates started to rise 2 weeks ago. We have clear plans for future work. Our team is developing the so-called karass model, which, unlike all other known models, allows to describe the multi-wave behavior of the epidemic. In the future, it will be possible to preserve the architecture of the approach discussed here, but replace the SI model, a parabola and a hyperbolic tangent, with the karass model. Thank you for your attention. I am ready to answer questions.